Okay, so let's just keep going with the material. This is where we begin to switch gears and talk about inferential statistics. So, if you remember when we started off this course, we said, okay, so the big roadmap is that at the end of the day, with statistics, we're trying to make sense of data, right? So, when we try to make sense of data, we spend the first 3.5 weeks of the course basically talking about, given that we have a raw data set, how do we begin to sort through it, to organize it, to start to make sense of it, to calculate some summary statistics about it, just to get a feel for the data, to how to graph it, how to visualize it, so on and so forth, right? That just told us what the data set itself looked like, what the basic contours of the data set were, right? Then we moved on and then we talked about probability theory, right? That was the bridge that we said between descriptive statistics and then where we headed off into inferential statistics. Because at the end of the day, if you really think about what the goal of statistics is to make sense of the world, to draw inferences about the state of the world using available data, right? So data is usually limited in a certain sense. There is a massive limitations on how much data we can actually possibly collect and how much we can analyze. The second piece of it is obviously getting much simpler with computing power. We can analyze massive data sets, and that's a good thing. But data collection still remains a bit of an issue. That's one thing. So we still need to take that into account. The second thing, which I like to emphasize before we move into inferential statistics, is just because the data might be available, it's not always uh, easy to make the best sense of that data, right? So there is a line which goes, "Data is cheap, meaning is expensive," and I subscribe to that notion quite heavily, right? So that's where the art of you as a statistician comes in. That's where you step in. That's where you work off a theoretical model or some level of intuition, some level of common sense to look at the data, look at what the data is predicting or saying or inferring about the state of the world, and then you apply a common sense test or you apply some kind of theoretical framework around it and say, within the context, within the confines of this theoretical context or within the confines of a um, of my intuition or my common sense, does it still make sense? Does the prediction make sense? So just because the data says something, you can't blindly accept it as faith, because as we said, data is incomplete in most cases, right? So that's my quick cautionary uh, tale before we get started. Okay, so we'll move on and get into the meat of inferential statistics starting now for the till the end of the semester, and we'll begin talking about some interesting features, right? So the first thing that we want to talk about is what we call normal distributions. Let me just get the pen here. So we'll talk about a class of distributions that are called normal distributions and a subclass of the same distribution, which is known as the standard normal, right? Uh, we want to get deeply familiar with normal distributions because it's very useful, right? It's one of the most useful distributions out there because it has some very nice desirable properties, right? If we can understand normal distributions, then we can begin to branch out and understand other kinds of distributions, right? So the normal distribution is like the de facto gold standard of, easy distribution to understand, to study, which has a lot of very desirable properties, and it's very widely used in statistics. So it's important to get this right, right? To make sure that you understand what a normal distribution is, how to standardize a normal distribution, and that's all good and well. But the place where the rubber meets the road, in essence, is where we begin to use these normal distributions to find probabilities and then find values. I'll talk about what it means to find values in just a few minutes, but that's basically the crux of it, right? Once we have a distribution in mind, we can begin to calculate areas under the distribution, and then that gives us a sense about what the probabilities are. Okay. Finally, this is the big jumping point of point into inferential statistics, is to talk about sampling distributions and a very key result inside of inferential statistics, what's known as the central limit theorem, right? So that's basically the roadmap. This entire discussion around these four topics should be covered in about 2 weeks' time. So this week and the next week will be on chapter 5, and then we'll keep moving the material. Okay. All right. So let's get started. Let's talk about normal distributions and standard normal distributions, right? So before we get into that, first let's just go back to the preliminaries, right? So remember, all of this discussion first begins with the notion of a random variable, right? Random variable is very well defined. It's a nice term for it. So remember, a random variable is first of all a variable that it takes different values, and it's random in the sense that it'll take each of these different values with different probabilities. That's what makes it random, right? So that's the first two bits of it, the randomness and the variable part of it. The continuous part of it comes down to asking the question, are the number of outcomes that this variable can take finite or infinite? Right? It's a way of saying, are the number of outcomes that this variable can actually take countable or not countable? If it is countable, which is what we did last week, talked about, we called it a discrete random variable. And if it's not countable, then we have a class of random variable that we call a continuous random variable, right? So for instance, if you think about the hours spent studying in a day, it could be anything from 0 to 24, right? And there's a lower limit and an upper limit. But it could be anything in between these 2 points, right? So you could have spent 0.0001 of an hour studying, you could have spent 0.5 hours studying, you could spend 0.77 hours studying. In a certain sense, between any 2 points on the number line, there is an infinite number of points in between these 2 points, right? So this is a variable which takes on many different values. It will take on each of these values with different probabilities, and the number of values that it can take on is not countable, right? So that's what we mean when we say a continuous random variable, right? All right. So a continuous probability distribution, again, remember, probability distribution basically lists all the values that the variable can take. It lists all the probabilities with which the variable will take any of these values. And for a continuous probability distribution, that's basically what you have, right? For each of these values, for this infinite number of values, we can essentially calculate the probability with which the random variable will take on each of these values, right? So given that that's the preliminaries, let's talk about one of the more popular kinds of continuous probability distributions, what we call the normal distribution, right? So first of all, a normal distribution is a continuous distribution. That is to say, between any of these 2 points, between any 2 points, there's an infinite number of values that the random variable x here is the random variable, and x can take any of these values on this number line, and and there's an infinite number of points on this number line, right? So it's the most important continuous probability distribution, right? And this curve that I've drawn here, this bell-shaped curve, we'll talk about the properties of this in just a second. This is what we call a normal curve, right? This is the curve which is the curve of a normal probability distribution is what we call a normal curve, okay? So let's talk about some properties of the normal distribution, okay? First of all, a normal distribution is symmetric, okay? So it's a symmetric distribution. We already know what symmetry means. Symmetry means that if I draw a line through the center of this distribution, then the entire distribution cleaves into two equal halves, which look like mirror images of each other, right? That's what it means to have symmetry. Left hand, right hand symmetry, if for instance, that's a classic case of chirality or symmetry, where basically you have two equal, in every way, essentially the same object on either side, but they're mirror images of each other, right? So in that sense, first of all, the normal distribution is symmetric. The way we verify if a distribution is symmetric or not is to check whether the mean, the median, and the mode are equal. And for a normal distribution, that should be the case, that the mean, which is the average, the median, which is a 50% value, and mode, which is the value which occurs with the highest frequency, all these three measures of central tendency are all equal, right? So if I look at the center of the distribution, that's where the mean, the median, and the mode are all located, okay? The second thing is that the shape of the curve itself, this is a bell-shaped distribution, right? So, it looks like a bell, right? So we call it a bell-shaped distribution, and it's symmetrically distributed around the mean, right? We already established if the mean, the median, and the mode are equal, then it stands to reason that the distribution is going to exhibit symmetry, right? So the normal curve is bell-shaped and is symmetric about the mean. The total area under the curve is equal to 1, right? So if I calculate the total area under this curve, it's basically equal to 1. All right. Why should that be the case? So if you imagine in the discrete case, we had something like this, right? That the sum of the probabilities, it's hard to write with this, but in the discrete case, when we had a discrete probability distribution, the sum of the probabilities was always summing to 1, right? Which is to say, if I have a random variable and I know all of its outcomes, then the random variable is going to take one of these outcomes as its value, right? So the sum of the probabilities with which the random variable will take one of these values is always 100% of the time. The random variable will be one of these values. That's what it means for the sum of the probabilities to be equal to 1. It's essentially a way of saying that this random variable x will take one of these values 100% of the time. It'll take each of these values with differing probabilities, but 100% of the time, it'll take one of those values which are available for x. In the continuous case, it's a similar story. If these are all the different values that x can take, then the sum of the area under this curve, because if I think about how I would graph it, if this is the value, sorry, my bad. Okay, so so let me get a pen. Okay, so if I think about a particular value here for x, the height here is going to basically represent the probability. So think of it as a small histogram, right? It's just a small frequency distribution. So minute, it's basically it's a pinpoint. It's like a shard, right? It's not a rectangle. So it's like a rectangle which is collapsed into a single spike, right? So in a certain sense, if I think about what the probability is, so I'm measuring the values of x on this axis, I'm measuring the probability on the y-axis. So the height here should represent the probability, right? So it's as if I'm saying if I sum all these different rectangles together, if I sum the areas of all these different rectangles together, that's the total area under the curve. So x can take any of these values, but it'll take one of these values 100% of the time. It'll take each of these values with different probabilities. That's why we have different heights for each value of x, but 100% of the time, x will take one of these values, right? So that's the reason the total area under the curve is equal to 1, right? So this is a continuous variable. So instead of a sum, which is what we do in a discrete case, we would have to take an integral, right? So that's beyond the scope, you don't need to know how to take the integral to get to the area. I'll show you an easier way of calculating areas for a normal distribution. But in general, in the general case, that's what you would do, right? You would essentially take the integral. All right. The next key feature of a normal distribution is that the normal distribution on either side, as on either side, gets closer and closer to the axis, right? It gets really close to the axis without ever touching the axis, right? So as I go further and further away from the mean, as I start from the mean, it's as if I start from this summit and I start walking down this gentle slope. And as I go further and further and further and further out from this distribution, it never hits the axis. It never intersects with the axis. It just keeps going off like that into infinity, right? It's the same on either end. So the tails of the distribution of a normal distribution never intersect with the axis. They just keep as it keep getting close in a formal sense. Asymptotically, they get very close to the axis, but there is always going to be, so if I blow this distribution up right here at the tail, if I blow it up, there's going to be a small gap between the tail of this distribution and the axis itself, which is to say that it will never touch the axis on either end. It'll just get arbitrarily close to the axis. It looks like it is basically touching the axis the way it's drawn here, but that's signifying that the further you go from the center of the distribution, the values get rarer and rarer, and the probability basically collapses close to zero, but it never is exactly zero. It'll be basically very close to zero. Okay. All right. So the last big property to recognize about a normal distribution is these 2 points that we call inflection points, right? Inflection points. Inflection in general is a fancy way of saying where the gradient changes, where the slope is changing, right? So if I think about, visualize this in your head, it's going to be an easy way to think about the distribution itself. Suppose you start off at the top of this distribution, you start walking. So this is like a mountain slope, you're at the top of this distribution, that's where the mean is at, and you start walking down this distribution, right? So as you start walking down the distribution, initially the gradient or the slope is really steep, right? It's a very, very steep slope, right? And initially the slope of the distribution is going to be rather steep. But as you start walking further and further along this distribution, it's going to start to level out, right? It's as if you start at the top of a mountain, initially the descent is really steep, and then as you go further and further down, it begins to level itself out. The point where it starts to level itself out on either side of the distribution, because it's symmetric, these are what we call inflection points. This is where the slope in a formal sense changes direction. So if I calculate the slope, if I draw tangents at different points here and calculate slopes, these are points at which the curve changes character or changes slope, right? So that's the first thing to recognize, is that if I start walking from the top of the distribution down to the tail of the distribution, initially the gradient is really steep and it begins to level out. And the point at which the curve starts to turn, right? These are turning points. Inflection points are also a fancy way of saying turning points. This is where this gradient is turning, it's changing, the slope is changing, right? And so we have two inflection points, one inflection point on the right side of the distribution and the other on the left side of the distribution, right? So there's two inflection points on either side of the distribution. Now, one nice property about the normal distribution is that we know what the location is of these two inflection points, right? So starting from the mean, if I take one standard deviation step to the right, I would find the right inflection point. And starting from the mean, if I subtract the standard deviation of this distribution, then on the left, that's where I would find the inflection point. So the two inflection points are located one standard deviation steps to the left and to the right of the mean, okay? All right, so those are some basic features of a normal distribution. I hope it's clear. All right, so let's keep moving with this. So now, one crucial thing here about normal distributions, these are distributions which are usually classed as bivariate, right? I've already talked about this in earlier lectures. Bivariate means that variate to a variable and bi meaning two, right? These are distributions which are basically defined by two key variables. So if I know two variables, I can basically trace out the entirety of the distribution, right? So a normal distribution, and the two variables that give me basically everything I need to know are the mean. So you tell me where the center of the distribution is, and standard deviation. You tell me how the rest of the data is spread out around the mean. If you give me these two key statistics, the mean, the center, which establishes where the center of the distribution is, and the standard deviation, which tells me how the rest of the data set is spread around the mean, I can describe the entirety of the distribution using only those two things, right? So a normal distribution is a class of a distribution which is known as bivariate, in the sense that it's completely defined, it's completely well defined by only two variables, the mean and the standard deviation, okay? So normal distribution can have any mean. So it can be positive, it can be negative, it can be zero, it can be whatever it comes out to be. It doesn't really matter. And standard deviation is going to be positive, right? And this is basically straightforward. Remember standard deviation. The standard deviation is the square root of the variance, right? So when we calculate standard deviation, is going to be the square root of the variance. So because it's a square root, we only consider the positive square root. So that's the reason why standard deviation is always positive, right? So because just by construction, standard deviation is the square root of the variance, and so we only consider the positive square root, and so the distribution can only have a positive standard deviation. Okay, all right. So these are bivariate distributions in the sense that the mean gives us the location of the line of symmetry. It tells me where the data set cleaves into two equal halves. And the standard deviation tells me how the rest of the data is spread around that line of symmetry. All right. So here I have three different distributions, right? So I just want to establish that you get why these are bivariate in a certain sense. So let's look at the first one. So the first one, the mean is 3.5. So it tells me that the center of this distribution is at 3.5 and the standard deviation is 1.5. So starting from here, I can trace out the rest of the distribution just using these two quantities. But the crucial thing is to recognize the inflection points for this uh, distribution are going to be one standard deviation step to the left and one standard deviation step to the right of the mean. So if the mean is 3.5 and the standard deviation is 1.5, so I start at 3.5, subtract 1.5, and that's how I get to the inflection point on the left side of the distribution. And if I start at the mean and I want to get to the right inflection point, I add 1.5, that's the standard deviation, and then I get to the right inflection point, right? So those are the two inflection points, and that's how I essentially figure them out, okay? So the second distribution has the same mean, which is to say we know that the center of this distribution is going to be at 3.5, but the standard deviation is 0.7, right? So if I compare these two distributions, they have the same center, the same mean, right? They have the same mean, but they don't have the same standard deviation. The standard deviation in the second case is smaller than the standard deviation in the first case, which means that it will generate a narrower distribution. Remember, the standard deviation is the measure of spread of the data around the central tendency, around the mean. So if they both have the same center, but one has a smallest standard deviation than the other, is going to generate a narrower distribution. Okay, and that's what we find, right? So starting at the center, if I want to locate the inflection points, I take one standard deviation step to the left. So 3.5 minus 0.7, that's 2.8. So the standard deviation on the left is located at the inflection point on the left is located at 2.8. And starting from the mean, I take one standard deviation step to the right, which means that 3.5 plus 0.7, that's 4.2. That's where the other inflection point is located. Okay. So that's one key thing, to understand how to interpret means and standard deviations, to understand what the interpretation is. It's easy enough to calculate these numbers, but it's important to know how to interpret the numbers themselves. And this is a case where, I have a similar distribution. This is a case where these two distributions have the same standard deviation, but they have differing means, right? So the mean is not the same. So in this case, the mean is a 1.5, so the center of this distribution is going to be a 1.5, but the shape of the distribution is basically defined by the standard deviation, so it's going to look very similar. So the shape of the distribution is the same, it's only shifted. In a certain sense, it's like I take this distribution, move it over to 1.5 and plop it down again, right? So as if I pick it up, move it over to 1.5, center it around 1.5, and I hinge it there. So I just lay the distribution on that pivot. Okay. All right. So here's a couple of quick examples just to make sure you understand. So you have two distributions, A and B. The question is which of these has the greater mean, okay? So the mean of the distribution is defined by the center. So for distribution A, the mean is at 15. For distribution B, the mean is at 12. So the curve A has a greater mean. The line of symmetry for curve A occurs at 15. That's what gives me the location of the mean. And the line of symmetry for curve B is located at 12, and that's where the mean is located for distribution B. Okay. All right. The second thing is that which curve has the greatest standard deviation. Now, I can eyeball it. If I look at the shapes of these two distributions, A is much more narrowly distributed around its mean, right? It's a much narrower distribution relative to B, right? The distribution B is much more spread out, right? It takes values over a much wider range. So it tells me that curve B has a greater standard deviation. The more the spread in the distribution, the higher the standard deviation is going to be. Right? So this is just to make sure that you understand intuitively what the mean and the standard deviation as measures represent about the data set. Okay, what they're telling me, what crucial information they're conveying about the data set itself. Okay, all right. So we can, in a certain sense, if I just have the distribution, in a certain sense, I can estimate the means and the standard deviation just by eyeballing distributions, right? So I might not have the statistics at hand, but if I have the distribution itself and a properly labeled axis, I can usually try to eyeball what the means and standard deviations are. How would I do that, right? All right, identifying the mean is straightforward, right? I just look for the center, the approximate center of this distribution, draw the line of symmetry through there. Well, draw a line of symmetry through there. Okay, the 650, that's 700, and the scale seems to go by 10. So the 660, 670, this is 680. So it's located somewhere halfway between 670 and 680. It gives me an indication that halfway between 670 and 680 is about 675. So given just the distribution itself, I can eyeball the mean by just looking at the center of the distribution. In this case, it's about 675. Okay. Now, getting to the standard deviation is basically a little bit more difficult. It involves a little bit more eyeballing. This is not as precise, right? So what I'm trying to locate for is that as I travel from this from the top of the distribution down the slope, where is the point at which the curve seems to level itself out, and seems like right about there the curve is shifting, right? Like right about there the curve is changing direction. So if this is the inflection point, so suppose, so this is the inflection point is at 710. Okay, so the inflection point is at 710, the mean is at 675. So I know that the right inflection point is located one standard deviation step away from the mean. So if the mean is at 675 and the right inflection point is at 710, the difference between these two is going to tell me the standard deviation. So the 710 minus 675, so I can eyeball that the standard deviation is about 35 for the distribution. I could do that on the same on the left tail, right? So starting from the mean, I can try to start from here and see where the curve changes direction. It seems like right about there, the curve is changing. So if this is my inflection point on the left, so this is going to be at 640. So the inflection point on the left is at 640. The mean is at 675. So 640 minus 675, that tells me again the standard deviation is about 35. So uh, in general, right, if I don't have the data readily available to calculate the mean and the standard deviation, but I know what the probability distribution itself looks like, then I can use that to basically eyeball or to approximate what the mean and the standard deviation for a normal distribution are. Okay, so that's the story with the normal distribution. Straightforward. A few things to remember, of course, that first is continuous, that the number of values that this variable can take are infinite. Second thing is that it takes a bell-shaped distribution. The curve is itself bell-shaped. The center of the distribution is located at the mean. It's symmetric, which means that the mean, the median, and the mode all agree with each other. It's bivariate in the sense that it is defined completely by two variables, the mean and the standard deviation. And there's 2 points of particular interest for us, which are known as inflection points. This is, or change points. This is the points where the curve begins to change character or the slope begins to change. And these are or change direction. I should be very precise. The slope begins to change direction. The gradient begins to level itself out. And those are what we call inflection points, and they're located one standard deviation steps to the left and to the right of the mean. Okay, so that's basically all you need to know about the normal distribution as far as the principles in statistics class goes. There's more to it. You go on to take more advanced classes in statistics and econometrics. You learn, we develop the ideas much more in those contexts. But this is the basic, absolute fundamental basics, bedrock basics of a normal distribution. And considering how widely used it is and how important it is in statistical analysis, it's imperative that you just get this right? That you completely understand what we mean when we say a normal distribution. Okay. All right. I hope the discussion so far is clear, and we'll keep moving forward. All right. Now let's talk about a very specific kind of a normal distribution, what we call the standard normal, right? So it basically builds off everything we know about the normal distribution, but it's a standardized form, and we'll figure out how we standardize this. Okay. A standard normal distribution is, first of all, it's a normal distribution, which is to say it follows all the properties of a normal distribution that we just recounted a couple of seconds ago. But the two key features of a standard normal distribution are around its mean and its standard deviation. So a standard normal distribution is first of all a normal distribution, this bell-shaped symmetric distribution where the area under the curve is 1, but it has a specific mean. It has a mean of 0, so it's centered at 0, and its standard deviation is 1, right? So the standard deviation is 1, okay? So the inflection points for a standard normal distribution are located at -1 and +1. Why is this the case? So if the center is 0 and the standard deviation is 1, the inflection points are located one standard deviation to the right and one standard deviation step to the left of the mean. So 0 plus 1 is 1, 0 minus 1 is -1. And so the two inflection points on this curve on either end are located at -1 and +1. Okay. Now we can start from any kind of normal distribution and get it into a standard normalized form using what we've already seen before, the z-score. Okay. So what the z-score is doing is, in a certain sense, what we call normalizing or standardizing. So that's where the name standard normal distribution comes from. It's standardizing the distributions. What does it mean to standardize it, right? So if I think about z-score, just intuitively, there's a formula, but let's first step back and see what the formula is saying. This z-score is saying if I pick some value x here, right? If this is the value x I pick, okay, right? So the first thing is to ask the question, how far is x from the mean, right? So I want to know the difference between where x is located and where the mean is. Okay, so if I think about, okay, so suppose x is measured in dollars. Okay, so if x is measured in dollars, x is in dollars, mu, the mean is in dollars, so the units here are in dollars, right? So both are measured in dollars, the difference is also in dollars. Okay, now this tells me how far x is in relation to the mean. That's what the numerator is measuring, the distance between a value and where the mean of the distribution is. How far is it from the typical value inside the distribution? Now the standard deviation tells me the spread in the data. So if I divide the distance by the standard deviation, it tells me how many standard deviation steps do I need to take to get to this value x, right? Because if this is the distance, so think about what it means in a very intuitive sense, and you'll never forget this, I hope. Because the formula will fall out of your head as soon as you take the final exam, and that's the end of that. But the conceptual understanding of what a z-score is very important, right? And I hope that you really take it with you out of a classroom, and when you go out there, you can think about z-score in that. So what it's saying is that if this is the distance between where x is and where the mean is, and I know the standard deviation, then it tells me this is the distance, the standard deviation is the step size, So the z-score measures the number of steps I need to take starting from the mean to get to this particular value x. Okay, so if you think about the units here, x minus mu is measured in dollars, suppose, and standard deviation is measured in dollars. The dollars cancel, so z is a unitless measure, right? That's what it means to standardize it, because now it will let me compare between distributions which might have different units of measurement, right? If one distribution is measured in apples, the other distribution is measured in oranges, is the classic case of I can't measure apples against oranges. But if I take whatever the distribution in apples and convert them into their relevant z-scores, or to take that normal distribution and standardize it, then I get a series of z-scores which don't have units. Okay, so I take the apples distribution and standardize it by converting each of those values into z-scores, and now I have a scale which doesn't have units. I take the oranges distribution, I convert it, that entirety of the distribution, into the z-scale. It's as if I swap out the x scale. So instead of x, I'm basically swapping it out for a new scale that I'm using, new axis that I'm using, that I'm slotting in its place, a z-axis, right? And now because z doesn't have units, I can make comparisons across distributions because the units are rationalized, right? The units are standardized, and that allows for cross distributional comparisons. So I can't directly compare the mean and the standard deviation of an apple's distribution versus the mean and standard deviation of an orange's distribution. But I can compare the z-score of an apple's distribution with the z-score of an orange's distribution, because the z-score standardizes the units, it removes the relevant units. Everything is measured in terms of number of standard deviation steps away from the mean. Okay, this is a place where I really miss being inside a classroom, because it's much easier for me to show this to you on a blackboard or a whiteboard, but we'll do the best we can. But I really hope that conceptually it's absolutely stone cold clear as to what this z-score is saying. Z-score says, look at any value x on the distribution, look at how far it is from the mean. So that's what it says. So z is basically take the value of x, look at how far it's from the mean. That's the total distance I need to traverse. Sigma here is the standard deviation, tells me the step size. So if I take the ratio of the total distance I need to travel divided by the size of each step I can take, z tells me the number of steps I need to take from the mean to reach the value x. The number of standard deviation size steps I need to take from the mean to reach the value x. Okay. All right. Hope that's clear. Okay. Why we need this? Why do we need to standardize? I already talked about one reason why we need to standardize. So I can start from any normal distribution. So this is some normal distribution for a random variable, a continuous random variable x, which has a mean of mu and a standard deviation of sigma, right? So it has a mean of mu and a standard deviation of sigma. I can take any normal distribution and standardize it by just applying the z transformation, right? So I take a value of x. So if I need to take this value x here, right? So I take this value x, I look at the difference between that value x and the mean, that's what the numerator is measuring, and then I divide that by the standard deviation of x. So this is a standard deviation of x. So that tells me that equivalently on this axis, this is where that x will land up in terms of a z-score, right? So this is basically taking this x and mapping it into the z-space, right? In a certain sense, we are mapping from the x dimension into the z dimension, and the way we conduct the transformation is using the z-score. Okay. Now, this is not just to make your life difficult, it has a practical use. The reason why we want to standardize normal distributions is that, let's first talk about why we might want to standardize these normal distributions. So one thing I know is that the area under this curve can be interpreted as a probability. Okay. Makes sense. That the area under the curve represents a probability. If this is x, the y-axis is measuring the probability of x. So areas between any 2 points can be interpreted as probabilities. That much is straightforward. We've already seen a version of this. Now the question is, if I have to calculate this area, right? If I have to calculate this area, for every kind of x I find with its own value of mu and its own value of sigma, first I need to find the area under the curve. Then I need to apply an integral, a closed integral between these two endpoints, and find the area under the curve for every single kind of distribution. And it becomes quickly cumbersome because if you look at the formula for a normal distribution, if you're curious, Google it. It's an exponential, it's a negative exponential distribution, so you find the expression there. It's quite complicated to take the integral of it over and over again, right? But if we standardize it, we can always find the area once, right? We can find the areas for different ranges once, and then we can use that table over and over again. That's what we mean by the standard normal table. It's in the appendix of the textbook. I'll also post a file which consists of the standard normal table. You need to learn how to use it. You'll be required to use it on the exam. So you need to know how to read it. I'll run through a couple of examples to show you how to read it properly and correctly. And I'll post the standard normal table also on the Blackboard side. So make sure you know how to do that. But before we get there, the point is that instead of having to calculate these areas every single time I encounter a new normal distribution, I calculate those areas once in the standard normal case, and I take any normal distribution which is thrown at me and I standardize it first, and then I use the table that I have to basically find the areas under the curve. Okay, that's the reason why we use this transformation. That's not the only reason. As I said, there's other reasons we've talked about for why we want to standardize this normal distribution, but that's one key reason for why we might want to do this. Okay, so finally, in this section at least, let's take a look at the properties of a standard normal distribution. It basically follows along the same lines of a standard for any kind of normal distribution. Okay, first things first. So if you remember the sorry, if you remember when we talked about a symmetric distribution, we said that about within 3 standard deviations of a symmetric normal distribution like this, right? Within 3 standard deviations, and this is going back to chapter 2, right? Within 3 standard deviations of any kind of this symmetric distribution, about 99.7% of the data is located, right? It's the empirical rule, the 68, 95, 99.7% of the data of rule that we talked about, right? So it tells me that between -1 and 1, which is one standard deviation steps away from the mean, in this range, about 68% of the data is in this range, 95% of the data is in this range, and 99.7% of the data is in this range, right, within 3 standard deviation steps from the mean. So with the standard normal distribution, we arbitrarily cut it off at -3.49. In reality, the distribution keeps going. It never hits the axis, but we arbitrarily cut it off at -3.49 because by the time we hit -3 or +3, so on this end we'll cut it off at 3.49. By the time we hit -3 or +3, we already covered 99.7% of the data. So if we keep going further, there is very little mass, mass left in the tail, so it's basically you can approximate it as if it's hitting the axis at 3.49 and you get a close figure, right? So one thing is that when the cumulative area is close to 0, when we hit these endpoints, right? So that's one reason why the table starts at -3.49 and cuts off at +3.49, because beyond that basically there's very little data left, because within this range of -3 to 3 we should have already covered 99.7% of the data set. Okay. All right. The second thing to take into account here is what we call cumulative area. Again, this is statisticians are precise, so the definitions are precise as well, right? So with cumulative area, as it suggests, it's cumulative coming out of accumulation, right? So one way to think about it is that if I start at this end at negative 3.49, I've not accumulated much area. So when I start traveling from negative 3.49 along this direction, I start to pick up more and more area under the curve. But when z scores are close to the negative 3.49, basically the cumulative area is zero, very close to zero. It's not exactly zero, it's negligible, right? It's close to zero. But as I travel further and further from the left end of this distribution, as I go further and further, I start to pick up more and more and more of this area, right? I start to accumulate more and more of the area. So the cumulative area increases as the z-score increases. So as I move in this direction, I accumulate more and more of this area, okay? So I suppose I start from this end of this distribution and I start traveling, right? So I accumulate more and more and more and more of this area. So by the time I hit zero, zero represents the center of the distribution, the cumulative area should be 0.5, right? By the time I hit the center of the distribution, I should have covered 50% of the distribution. So the cumulative area under the curve between the left end point, which is cut off at negative 3.49, and the right end point, and this point, which is 0, so the right end point as the mean, is going to be 0.5. So there is about half the area is located between these two points, right? And then I can keep going further and further and further, and by the time I hit negative 3.49, I should have accumulated all the area under the curve. So basically the cumulative area is close to 1 for z-score is close to 3.49, right? So that's the notion of cumulative area, okay? So it's an important idea. It's the first time you see these things in statistics is easy to get confused, but just if you can imagine, keep this picture in your head, that cumulative area, first of all, the name itself says cumulative, so it's accumulation. So when I start from the left end, initially I don't accumulate a lot of area, so that says that initially the area under the curve for values of z-score close to negative 3.49 are going to be negligible, are going to be quite close to zero. But as I travel further and further from the left end point to the right end point, I start to accumulate more and more and more of this area. So when I hit the halfway point, I should have accumulated half the area. And by the time I hit the end point, I should have accumulated all of the area, or the area under the curve. The cumulative area under the curve at that point is 1. Okay. All right. So one thing I want to mention here, let me see if I can. Okay. One thing I want to mention here is that why do we care about cumulative area, right? Okay. So if I ask the question, what is the probability with which I get a z-score of 1? Okay. So in a discrete case, all I would do is try to draw a histogram, a frequency histogram around the value 1, calculate the area of this rectangle, and that would tell me the probability with which x will take a value of 1, right? That's what I do in a discrete case. But in a continuous case, there is a rectangle here, but there is immediately right next to 1, there is a value which is also a plausible value, right? So it's continuous, so 0.999999 is right there, and it has its own probability. Which is to say, if I think about this, at any given point, I don't get a rectangle anymore, I get a spike. Okay, so basically it's as if I have like a sharp spike going up. So if you can imagine, one way to drill this into your head is to think of this as icicles, right? So it's as if I start at this point and then a sharp icicle, it's very thin, it's razor thin, it's basically, you can't, it's the thinnest slice of an icicle that you've ever seen hanging off here. So it's like a spike. If it's a spike, to calculate areas, I need length and breadth, right? In general, area is length times breadth. For any kind of object, any kind of regular object, area is length times breadth. This is an entity which has only length but has no breadth, right? Because it's a pinpoint shard. It's a sharp spike which is rising, but it doesn't cover any area. Okay. So in that sense, I can't really talk when I talk about continuous probability distributions. I can't really speak about the probability of any particular value. I can only talk about cumulative areas. That's why cumulative areas are important, because it defines areas or probabilities for certain ranges, right? All I can talk about is the probability in this range, the probability that z will take, or I get a z-score of any particular value, is hard to fathom, right? Because I just get a sharp spike there, right? It's a bit advanced for a principal statistics class, but I really want to build the intuition out that that's what's happening. That's the reason why we are calculating cumulative areas and not calculating the areas for any of these values directly, because we can't calculate the areas for any of these values directly, because all we have are sharp shards and they're razor thin. So if it's razor thin, it's like a thin, the thinnest iron filament, right? If you ever seen a filament of iron, it's so thin that it's almost you can't see it with the naked eye. It's that thin, right? And I asked the question, how much area does this filament take up? And you say, I don't know, it takes up some non-zero amount of area, but it's basically close to zero, right? All right. So the last thing for this section at least is to learn how to use the standard normal table. Okay. Two things to bear in mind. The standard normal table, okay, reports cumulative area. Okay. What does it mean? All right. So let's look at an example here. So if this is my z distribution, this is where I miss Blackboard immensely, but okay. So suppose I have a z distribution, right? So for a z-score, the way to read this is this 1.1. So these are the first two digits. So that's the first one. This is the first digit after the decimal, 1.1. And then read then go to the right column. So the way to read this is z-score of 1.15. Okay, so this is basically a z-score of 1.15. So if this is 0, so the center of this distribution is a 0. So 1.15 is here. What the table is telling me is cumulative area. Cumulative area in the sense that if I start at the left end of this distribution and I travel to 1.15, how much area would I have covered? So it is always going to tell me the standard normal table is always going to tell me areas to the left. That's crucially important to recognize, that the table is always telling me cumulative areas, and the accumulation is going to start from the left tail on. So what this means is that if I start from the left tail, the way to read this is that if I start from the left tail of the normal distribution and walk my way all the way up to 1.15, I would have covered 0.8749 or 87.49% of the area under that curve. Okay, so that's the way to read these tables. I'll post the table on Blackboard, and you'll have plenty of practice using the table and calculating these probabilities on the homework. But it's critically important to recognize that what the table is reporting is cumulative areas, and by cumulative areas we are talking about areas which are accumulated when you start from the left end of the distribution and travel up to whatever z-score. And the way to read this is a z-score of 1.1, and the column tells me the second decimal point, right? So it's 1.1 and the second decimal is 5, so this is read off as 1.15. So if I start from the left end of the distribution and travel up to 1.15, then the area up until there is about 0.8749. Okay. Similarly, it's on the negative side, right? Negative 0.24. So in this case, z-score of negative 0, so it's negative 0.2. And if I want to read of the second decimal, so this is read off as negative 0.24. So what this says is that if I start from the left end of the distribution, so again, it's the same kind of story. So I have okay, that's terrible, but you get the idea. So that's 0. So if I start off at the left end of the distribution and then I travel up to negative 0.24, 0.24, so I start covering some area, and by the time I get to 0.24, the area to the left of this negative 0.24 is 0.4052, right? So which is to say I would have covered about 40.52% of the area under the curve by the time I got to 0.4, by the time I got to negative 0.24. Okay. So make sure you play around with these standard normal tables. There's enough practice on the homework, but it's crucial that you understand that one, it reports only cumulative areas, and then you can only read areas to the left. So what happens when you need areas to the right? That's where we're going next, but that's basically what it is. Okay, that's the first key thing as to how to read the table itself. All right. The second thing, right? So, okay, no. Let me just, this is the standard example. So 1.23, suppose I have a z-score of 1.23. So I would go to the standard normal table. 1.2 is what is the right row to look up. 0.03 is the right column to look up. So if I go look inside the z table and look up the score of 1.23, I'm going to leave this for your exercise. So download the standard normal table that I put up on Blackboard and then make sure that the numbers come out and you're able to read it right. So if I look for 1.23 inside that table, then the area which is listed there is about 0.8907. So the area to the left of this value is about 0.8907. Okay. So what happens if I want to find areas to the right? Right. So, okay, I know this area from the table. So what happens if I want to know the area to the right of negative 1.23? And it's basically straightforward. If the total area under the curve is 1, which is what we know, and if this area here is 0.8907, so if I've already accumulated 0.8907 worth of area by the time I started from the left end and got to 1.23, the area to the right tells me how much further do I have to go, right? So if the total area is 1, and I've already covered 0.8907 by the time I got to 1.23, then the area to its right is basically the total area minus the area to its left. That's what the area to the right is, right? So I take the total area is 1, subtract the area to the left. This number I get from the standard normal table. So the area to the right is the total area, which is 1, minus the area to the left. Because total area at the end of the day, intuitively, area to the left plus area to the right, there's only two directions, right? So it's left or right. So the area to the left plus the area to the right is equal to the total area, and the total area is 1. So if I know the area to the left, then the area to the right is the total area, which is 1, minus the area to the left. Okay, that's how I calculate areas to the right. Okay. The last thing is basically about finding areas between two different in certain regions. So suppose I want to find the area between negative 0.75 and 1.23. Okay, all right. So what would I do? I would go to the table, I would look up 1.23, and it tells me that the area to the left of the area to the left of 1.23 is 0.8907. So that I know. Okay. Then go to the table again and I look up the area, the cumulative area for negative 0.75, and it turns out that the area here is negative 0.75. And it's the to the left of negative 0.75, 0.2266. So if the area from the left end to 1.23 is 0.8907, and the area from the left end to negative 0.75 is 0.2266, then the area in this region is basically this entire area subtracted, and from that you subtract this area out of it, right? So it's the difference of these two areas. So 0.8907, which is associated with 1.23, minus 0.2266, which is associated with negative 0.75, and that tells me that the area between those 2 points is 0.664. Okay. All right. So there's a few examples in the slides that you can go over and make sure that you understand. But that's basically all I have for the first section. So there's going to be two videos this week. This is part one, and then I'll post part two as well. So you'll have two 1 hour lectures for this week. So sections 5.1 is done here, and then I'll post the second part right away. Right. So you have about 2 hours worth of lecture to watch this week. All right. Hope things are clear. Again, use the comments thread below the video to ask any questions that you have while you're watching it. And, if there's any other questions, email me. Office hours will be back up from this week on Fridays. So, yeah, you can see me during office hours as well. All right. Okay. All right. I'll see you in the next video.